Hello, welcome back to Algebra. Today we're going to see the third and final Sylow theorem. So just as a reminder, what are the Sylow theorems? Here are the three Sylow theorems. We have a finite group G, let P be a prime, that is a divisor of the order of the group. P to the R is the largest power of P dividing the order of G. Then we have proof that there are subgroups of order exactly P to the R. If two subgroups are what we call P-Sylows, so subgroups that are that large, the maximal P group inside G, then if we have two P-Sylow subgroups, they're conjugates. That's what we proved last time. That's the second Sylow theorem. And then now we're going to prove the third Sylow theorem that tells me how many distinct P-Sylow subgroups of G are there. If I called NP, it doesn't tell me exactly how many are there. It gives me a little bit of a puzzle, but it's very helpful. There is NP is, first of all, 1 modulo P. That's a strong condition in terms of congruences. We've seen examples of using this, and it's very useful. And second, NP, the number of distinct P-Sylow subgroups, is a divisor of G. So let's prove this part, the third Sylow theorem. And just as a reminder, in 2 videos ago, we proved 2 preliminary lemmas, lemma 1 and 2, which we're going to use in the proof again. The proof of the third Sylow theorem is actually very similar to the second Sylow theorem proof. So let me show you how it goes. The proof goes as follows. Let P be P-Sylow subgroup of G. Remember that G is P to the R times M, with P and M relatively prime, and therefore the size of P is exactly P to the R. And now let P be acting on the set of all P-Sylow subgroups via conjugation. So here is S is going to be all the P-Sylow subgroups. P is 1, and then, well, I'm going to call P is going to be also P1. And then there are more, P2, PI, up to PK. And this K is actually the number of P-Sylow subgroups is in fact what we call NP, is the number of P-Sylow subgroups. I'm going to let P act on these via conjugation. And so there is an action of P on S that, because every conjugate of a P-Sylow group is another P-Sylow group, and it might not be the entire orbit. If this was under G conjugation, then there is only one orbit, because we know any two are conjugates by the second Sylow theorem. But since I'm restricting the conjugation to elements of P, then there's going to be blocks, okay? So there's going to be several blocks. We're going to see that this actually just goes to itself. And then there's going to be several packets, like I said in the second in the proof of the second Sylow theorem, which are the orbits of, say, Pi under conjugation by P, however many other P-Sylow subgroups are conjugate to Pi, that is that packet, that orbit of Pi under P conjugation. Okay, so some facts. Notice, first of all, I said that P is up on its own. So first of all, if X is in P, then X, P, X inverse is all in P, so I have to get P back, okay? So the orbit, that is, the orbit of the P-Sylow group P itself, so of P1, has size exactly 1. Okay, it's just the P-Sylow itself. Now, suppose I have another one of order 1. Suppose I have another orbit of order 1. Suppose the orbit of pi is just pi. Then what is happening is that for any x in P, x pi x inverse gives me back pi because there's only one P Sylow group in the orbit. So for all x in P, but one of our lemmas, lemma 1, I believe, from previous videos, this lemma exactly tells me what? If the order of x is a power of P, and x conjugates this P Sylow subgroup to itself, then x is in P Sylow to begin with. So notice that if x is in P, then because the size of P, the order of the P Sylow group P is a power of P, the order of x is some power of P, and therefore lemma 1 together with this implies that that x is actually in pi to begin with. But that would say that for all x in P, x is also in pi. That would imply that P is contained in pi, but this also implies that P equals pi. Why? Because they are both the size of P and the size of pi. Those are P Sylow groups. They are of the same size, so an inclusion implies an equality. So what this says is that the upshot of this is that the only orbit with exactly one element is that of P. Every other orbit has more than one element. Okay, so let me write that as a fact then, that if the orbit, if P I is not P, then the orbit of Pi is of size bigger than 1. All right, that argument we also did in the proof of the second Sylow, but I'm repeating it here so it's self-contained. All right, so now what's my next fact? The next fact we're going to need is something that we also used in the proof of the second Sylow theorem, but let me repeat it here, that I have P, which is P1, and then P2, and then Pi, and then all the way to P and P. And I have packets, I have orbits. That one is on its own. Every other orbit is larger than one, it has more than one P Sylow in it. And then we want to know, well, how many elements are there in each orbit? But that is exactly what lemma 2 tells me. Lemma 2 tells me that the number of P conjugates of Pi, so the size of the orbit, so the number of P conjugates of Pi, which is the size of the orbit of Pi under this action, is precisely given by P and the index of the intersection of the normalizer of Pi under G in G, the normalizer of Pi in G intersect with P. So this index gives me the number of however many P Sylow subgroups are there in this orbit, or the what we say the P conjugates of Pi. But also we have, thankfully, we have Lagrange, and Lagrange tells me that the size of P, which I know is a power of P, is the size of the subgroup of the intersection of P and that normalizer times the index of that subgroup. And since this is a power of P, that implies that this is a power of P. So what that means is that the upshot is that each block, each orbit of P conjugates of P Sylow subgroups is of size a power of P. And now we can use what we've called a class equation for this action on the set of all P-Sylow subgroups and get the following. So remember what we've called a class equation when we have a G set, so G acting on X, then a class equation is anything of this form. The size of X is going to be the size of the fixed points of X by the action plus the size of orbits, of distinct orbits under the action. Okay, so what we actually have in our case, we have S, the set of P-Sylow subgroups, and then I have P acting on the P-Sylows, and we've just found out is that S, this number of P-Sylows, that is exactly what I call NP, is going to be the first fact we've proved is that there's only one P-Sylow that is fixed under the action of P by conjugation, which is P itself. So there is only one there. And then what we have found out is that every other orbit, so this is the orbit of order 1, every other orbit is larger than 1, and each one of those is a power of P. So every one of these orbits is some power of P in size, P to the E1 plus a P to the ET, some different orbits, and each one of those with E1 up to ET are really bigger than 0 because none of those powers are 1. They are at least P. But that implies that this is a multiple of P, and then the number NP is 1 plus a multiple of P, so this is 1 modulo P, which is exactly what I wanted. Hence, NP is congruent to 1 modulo P as we wanted to show. So it remains to show now that NP is a divisor of the order of G, and we will do that considering a different action, but that is going to be easy to do. Let's do that now. So now to show that the number of P-Sylow subgroups actually divides the order of the group, what we're going to do is now consider G acting on S. This is the set of all P-Sylow subgroups. And since we know the second Sylow theorem now, the second Sylow theorem tells me that all elements, all P-Sylows are conjugate, are G conjugates, G conjugate. Therefore, there is one orbit in G acting on S. But by our lemma, we know also how many orbits are there. S, the size of S, which is the orbit of the one P-Sylow P we had. It is also the index in G of the normalizer of P. That is also the number of G conjugates of P are given by exactly this formula by one of our lemmas, and therefore this is this index, by the way, is also by Lagrange's theorem. We also have that G is the size of the normalizer. This is the normalizer in G of P times the index, like this, right? So this was by Lagrange. I have this, but then the upshot is that this number divides the order of the group, and therefore this divides the order of the group. So the number of P-Sylows, which is NP, divides the order of the group. Thus, NP divides the order of the group, which is what I wanted to show, and that proves the third Sylow theorem. Very good. So we have seen examples of how these are actually used in practice. And next, what I'm going to do is at least one or two applications to particular examples of classifying groups of a certain order using the Sylow theorems in a slightly more theoretical way and also more practical way with concrete orders. So we will do that in the next video.